बिस्मिल्लाहिर्रहमानिर्रहीम अस्सलाम वालेकुम। कैसे हैं आप? दिस इज लेक्चर नंबर 26. Let's start. So first we take a review of last lecture. In last lecture we have discussed the normal distribution, and in particular we discussed probability density function of a normal distribution, and then we have discussed some of the important properties of normal distribution, and we have also discussed some related examples. So now let us discuss the objectives of the current lecture. In this lecture we are going to discuss how we can calculate area under the normal curve, and then we will discuss several problems related to this finding area under the normal curve, and then in the end we will discuss normal approximation to binomial distribution, and we will illustrate this idea with the help of certain examples. So let's start. So before moving further, there is one very important property of normal distribution that is also called empirical rule. It states that the probability that a random variable x lies between mu minus sigma and mu plus sigma. So the probability that random variable lies within these two limits, it is 68%. So this probability is 68%. Or we can also state it as that within one standard deviation away, within one standard deviation of mean. So you can see that here the peak of normal distribution, it always occurs when x is equal to its mean mu. So if we go one standard deviation, that is sigma, 1 times sigma, to the right of mu, we get mu plus 1 sigma, 1 times sigma. And we can also go leftward, so it means we can subtract 1 times sigma from the mean to get mu minus sigma. So this means that the probability that random variable x lies within this range from mu minus sigma to mu plus sigma, this probability is approximately equal to 68%. So since normal distribution is symmetric, so this is the middle line, this vertical line at the middle, so this is symmetric, so it means this middle line divides the normal distribution, divide the area into two equal parts. So if this area between mu minus sigma and mu plus sigma is 68%, so it means area from mu minus sigma to mu, this will be 34%, and from mu to mu plus sigma, this will be the remaining 34%. So this 34 and 34, they will combine to get an overall area of 68%. So this is first empirical rule. So similarly, the second empirical rule states that if we move from the mean two standard deviations on either side of the mean, so that is if we subtract 2 times sigma from mean, we get mu minus 2 sigma, and if we add the same number, that is 2 sigma, to the mean, we get mu plus 2 sigma. So this second point, so the probability that x lies within these two limits from mu minus sigma to mu 2 sigma, this is equal to 95%, or we can say that 95% of the area lies within 2 standard deviation of the mean. So this means that within these 2 points from mu minus 2 sigma to mu plus 2 sigma, we have approximately 95% of the area, or 95% of the probability. So again, since normal distribution is symmetric, this is the middle line, so it will divide this 95% area into two equal parts. So such that this probability, this will be 95% divided by 2, so which is 47.5%. So similarly, from mu to mu plus 2 sigma, this will also be equal to 47.5%. So if we add these two areas together, we get the total area from mu minus 2 sigma to mu plus 2 sigma under this normal curve. So this is 95%. So the third empirical rule states that 99.7% of the area lies within 3 standard deviation of the mean, or in other words we can say that between mu minus 3 sigma and mu plus 3 sigma we have around 99.7% probability or 99.7% area. Remember that in case of normal distribution the probability is same as area. So we can use these two words interchangeably. So from mu minus 3 sigma to mu plus 3 sigma we have this portion between these 2 points, and this is equal to 99.7%, or the area or probability is 99.7%. So again this is the middle line, so it will divide this 99.7% probability into 2 parts. So in such a way that this probability from mu minus 3 sigma to mu, this will be half of 99.7%. So 99.7 divided by 2, and similarly this remaining portion, area between mu and mu plus 3 sigma, this will be the second half, 99.7% divided by 2. So these are the 3 empirical rules. From these 3 empirical rules, by using these 3 empirical rules, we can calculate probabilities between mu plus sigma and mu plus 2 sigma, or mu plus 2 sigma and mu plus 3 sigma, or mu minus sigma and mu minus 2 sigma, or mu minus 3 sigma and mu minus 2 sigma, or between mu minus 3 sigma and mu minus sigma. So let us explain it. Suppose we are interested in finding the area from mu plus sigma to mu plus 2 sigma. So from the empirical rule we know that the area from this mu to mu plus 2 sigma, it is 47.5%, and the area from mu to mu plus sigma, it is 34%. So if we are interested in finding this probability or this area, so this can be obtained by taking the difference of 47.5 minus 34%. So just subtract 34% from 47.5%, you will get 13.5%. So this is how you can calculate area within any 2 points. So similarly, since the normal distribution is symmetric, so area between mu plus sigma and mu plus 2 sigma, it will be same as area between mu minus 2 sigma and mu minus sigma. So this is also equal to 13.5%. Or again, by using the same logic, we know that area between mu and mu minus 2 sigma, it is 47.5%, and the area between mu and mu minus sigma, it is 34%. So if you are interested in finding this area between mu minus 2 sigma and mu minus sigma, so just take the difference, that is subtract 34% from 47.5%, you will get 13.5%. Okay, so we have area between mu minus 3 sigma and mu, that is half of 99.7%. So this is 49.85%, and similarly this is also equal to 49.85%. Now suppose we want to find area between mu plus 2 sigma and mu plus 3 sigma. So we are interested in finding this area. So in order to answer this question, we know that area between mu and mu plus 3 sigma, this is 49.85%, and area between mu and mu plus 2 sigma, this is 47.5%. So if you are interested in finding area between mu plus 2 sigma and mu plus 3 sigma, so just take the difference of these two areas. So 49.85 minus 47.5%, so you get 2.35%. So similarly here on right hand side we have the same probability or same area. So this is how we can use the three empirical rules to calculate different probabilities. Now let us discuss the cumulative normal distribution, which is also called the cumulative distribution function of a normal distribution. So for our normal random variable x with mean mu and variance sigma square, we can write it as x is normal, or x is distributed as normal with mean mu and variance sigma square. So then the cumulative distribution function is defined as f of x naught, it is equal to probability that random variable x is less than or equal to x naught. So we have already defined this cumulative distribution function, which is also called the CDF of random variable in case of binomial distribution and in case of uniform distributions as well. So now here we can define the CDF in case of normal distribution. So if we have a random variable which follows normal distribution, and the name of random variable is x, we can use any other symbol as well, usually x is used. So if we have a random variable x which follows normal distribution having mean mu and variance sigma square, so mathematically we write it as x is distributed as normal with mean mu and variance sigma square. Remember that these are the two parameters of normal distribution. The first one is mean, the second one is variance. So then the cumulative distribution function or CDF of x is defined as f of x naught, where x naught is any value of random variable x. So it is equal to probability that random variable is less than or equal to this value. So let us look at this diagram. So here if we have the bell-shaped curve, and suppose here is the point x naught. So CDF at point x naught is probability that x is less than or equal to this point. So it means we are interested in finding all this area, the red one, that the probability that random variable x takes values less than or equal to this value up to this value x. So it means this all values which lie in this red portion, they are included. So this is the overall concept of CDF, that it gives the probability that random variable x is less than or equal to that particular value. Here in this case the value is x naught. So finding normal probabilities. So suppose here is the bell-shaped curve, here is this mean of this distribution is mu, and suppose we have 2 points. So let us focus on point B. So suppose we are interested in calculating this probability that random variable x is less than b, or in other words we can state it as, we can write it as that this is CDF at x equals to b, or we can write it as f of b. So it is the probability that random variable x is less than b. So it means this full shaded area is our requirement in this problem. So we need to calculate this shaded area. So we can use the CDF to calculate this probability. Later I will explain how we can use Microsoft Excel to calculate this probability as well. So now suppose we want to calculate CDF of x at point A, that is f of a. So if we are interested in calculating CDF of f at x equals to a, that is f of a, this is equal to probability that x is less than a. So here is point A, so it means we are interested in finding this shaded area. So again this means that just calculate the CDF at x equals to a. Now we can use these two concepts to calculate the probability that random variable x lies between a and b, or in other words we are interested in finding the area between a and b, or this area which lies between a and b. This middle area is our required area. So in order to calculate this area we can use the concept of CDF. So note that CDF at point B, it gives us all the area which lies to the left of B. So it means it gives us this full area. And CDF of x, random variable x at point A, it gives the area to the left of point A. So if we are interested in finding this middle area between A and B, so we can subtract CDF at point B, which is f of b. We can subtract f of a from f of b. So if we subtract f of a, this probability, if we subtract this area from this whole area, so it means we are getting actually this middle area, which is the required area in this diagram. So in order to calculate probability that random variable x lies between a and b, so this is calculated as f of b minus f of a, where f of b is CDF of x at when x is equal to b, and f of a is CDF of x when x is equal to a. So this is how we can use the concept of CDF of x to calculate the area between the two values. So later we will do the Excel demo in which you will get more clarity on this concept. So now let us discuss the standardized normal distribution. Any normal distribution with any mean and variance combination can be transformed into the standardized normal distribution Z. Usually Z symbol is used for standardized random variable. So standardized mean, the mean is 0 and variance is 1. So if mean is 0 and variance is 1 and the distribution is normal distribution, so then we can say that we have a standardized normal distribution. So in case of standardized normal distribution, the mean should be 0 and variance should be 1. But if mean is different from 0 and variance is different from 1, then we say that this is not the standardized normal distribution, it is the general or simple normal distribution. So but if we fix mean at 0 and variance at 1, so then we have a special name for the normal distribution and we call it as standardized normal distribution. And consider another case, suppose mean is fixed at 0 but variance is different from 1. So again this will not be a standardized normal distribution. Or suppose if mean is different from 0 and variance is equal to 1. So it means one of the conditions is being satisfied, that either mean is 0 or variance is different, or variance is 1 or mean is different from 0. So these two conditions they are again not standardized normal distributions. So for a standardized normal distribution, the mean must be 0 and variance must be equal to 1. So usually we write it as using the symbol z. So z is normal with mean 0 and variance 1. So here is the diagram. So you can see the bell-shaped curve. So now this mu, mean of random variable x, is fixed at 0. So here the peak occurs at its mean. So mean is 0 in this case, and this spread is measured by the standard deviation, which is square root of variance. So it is equal to 1. So on x-axis we have random variable z, on y-axis we have the corresponding probabilities. So need to transform x units into z units. So how we can transform, how we can get standardized normal distribution. So in order to get standardized normal distribution, we have to transform the x random variable into a new random variable z. So this is obtained by subtracting the mean of x. If we subtract mean of a random variable x from each of the observations, so it means we are actually centering the random variable. So centering mean converting the mean or shifting the mean to 0. And if we divide the same random variable by its standard deviation, so it means we are scaling, we are adjusting the scale of the random variable, or in other words, we are actually making standard deviation to 1. So here is the formula which is usually used. We have discussed this formula in one of our earlier lecture as well. So z is equal to x minus mu over sigma. So if we subtract mu from x, so it means we are actually centering it, or we are making the mean of z to 0, and if we divide this expression by sigma as well, so it means we are shifting the standard deviation to 1. So now this z random variable, its mean will be 0 and variance will be 1. So we say that z is a standardized random variable with mean 0 and variance 1, or it is a standardized normal random variable, because the original variable x, it follows the normal distributions. So z is also normally distributed, and the mean is now 0 and variance is now equal to 1. So now let us consider an example to illustrate this standardization conversion case. So if x is a random variable which is distributed normally with mean of 100 and standard deviation of 50, so then the z value for x equals to 200 can be calculated by using this formula. Z is equal to x minus mu over sigma. So just replace x by the desired value, which is 200 in this case, minus mu, which is 100, divided by sigma, which is 50. So 200 minus 100, we get 100, divided by 50, so 100 by 50, we get 2 or 2.0. This is simply equal to 2. So this 2 means that x is equal to 200 is 2 standard deviations, that is the 2 increments of 50 units, because 50 is the standard deviation. So x equal to 200 is 2 standard deviations above the mean of 100. So mean is 100, so and current value of x is 200 and standard deviation is 50, so it means it is 200 is above this 100 value. How much? 2 standard deviations. So 50 times 2, so it is 100 above. So but in statistical language we say that 200 is 2 standard deviations above the mean. or since mean is 100, so we can say that 200 is 2 standard deviation above 100. So let us compare x with z units. So here we have the same bell-shaped curve. So mean is 100, and suppose here is the point x, which is 200, and here we have the mean 100 and sigma is 50. So this is the usual normal distribution. So after conversion, the mean of this distribution, it becomes 0, and standard deviation, it becomes 1. So it means we have a new variable which is represented by z. So z is a standardized random variable which follows normal distribution just like the random variable x. So now this 100 in terms of z units, so now mean is 0, so we say that now the mean of this distribution, this random variable z, is 0, and this 200, now in this case it is 2. So 200 is 2 standard deviations above this 100. So you can see that originally we have this scale mu 100 and the value of x 200. So but since the distribution has been standardized by converting mean to 0 and sigma to 1, so now we have the new numbers. So note that the distribution is exactly the same, only the scale has changed. So instead of 100 we will use in case of a standardized random variable 0, and instead of 200 we will use the number 2. So only there is difference in scales while the shape of the distribution is exactly the same. So we can express the problem in original units, that is in terms of random variable x, or in terms of the newly introduced standardized random variable z, which is also called standardized units. So we can express the problem in original units x or in standardized units z. So now let us discuss the standardized normal probability density function. So note that the formula for the standardized normal probability functions can be obtained by replacing mu 0 and sigma 1 in the original density function of random variable. So here this is the formula which gives us the density function of a random variable x, which follows normal distribution with mean mu and variance sigma square. So its density function is f of x equals to 1 over square root of 2 pi into sigma into e raised to power minus 1 by 2 x minus mu over sigma whole square. So if we replace this mu by 0 and if we replace this sigma by 1 here as well as here, so we can get a new distribution, new density function, which will be the density function of a standardized normal random variable. So if we replace 0, so x minus 0 is x, divided by 1 we get x, and then this square mean x square. So you can see that we get minus 1 over x square, and if we replace this sigma by 1, so we are left with square root of 2 pi only. So this is the simplified form, but usually instead of this random variable x we use the random variable z. So because z means that the random variable is in standardized units, where z is what? It is x minus mu over sigma. So f of z is 1 over square root of 2 pi e raised to power minus 1 by 2 z square. So this is the density function of a standardized normal distribution. So now finding normal probabilities, suppose we are interested in calculating the probability that random variable x lies within a and b. So in terms of standardized units, we know that the standardized random variable is z, which is x minus mu over sigma. So we can write the same question in terms of random variable z. So instead of writing using random variable x, we can use random variable z. So here we have a, so just replace this x by a. So we get a minus mu over sigma. So a minus mu over sigma, and here replace this x by b. So we get b minus mu over sigma. So in case of standardized random variable, the same question, that probability random variable x lies between a and b, it is written in this form, that a minus mu over sigma is less than z, which is less than b minus mu over sigma. So we already know that this probability is found via this by using the concept of cumulative distribution function, that is f of b minus f of a. So here again replace this b, which is b minus mu over sigma, minus f of a minus mu over sigma. So here we have this x scale. So here x is equal to its mean. So suppose we are interested in finding the probability between a and b, or finding area within these two limits. So in order to calculate this area, we can convert this a and b into new units. So let us introduce a random variable z, which is x minus mu over sigma. So b is b minus mu over sigma, and now mu will be 0 and a will be a minus mu over sigma. So you can see that only the scales have been changed, that is the variable a is transformed to get a new variable, b is transformed to get new variable, and where mu is transformed to 0. So now the question is exactly same, but if we convert the random variable x into random variable z, so we can calculate probabilities relatively easier. But since nowadays we have different software packages, especially in this course we are using Microsoft Excel. So Excel has a built-in function for calculating normal probabilities. So whether we use in Excel, we can use the random variable x formula in this original form, or the formula in case in standardized units as well. So we will see in this lecture when we will do the Excel demo. So probability as area, as I have already explained to you, that the area means the probability. So area under the curve is same as the probability. So we know that in case of normal distribution, the total area under the curve is 1. And since the normal distribution is symmetric, that is equally spreaded around the middle line, the mean line, so half is above the mean and half is below the mean. So here is the bell-shaped curve. So it means since we know that this x lies between minus infinity and plus infinity, so the probability that random variable x lies between minus infinity and plus infinity, this is equal to 1. So, or in other words, this is giving us the total area under this normal curve, this full area from minus infinity to plus infinity. So this is exactly equal to 1. And now since it is symmetric, so this is the middle line, the mu line. So we can say that at x equals to mu, so this is the line of separation. So on the left hand side we have the 50%, and on the right hand side we have the 50% area. So we can write it as probability that minus infinity less than x less than mu, it is equal to 0.5 or 50%. And similarly from this mu to plus infinity we have this 50% probability. So probability mu is less than x, which is less than plus infinity, it is also 50%. So if we combine area to the left of mean, which is 50%, and area to the right of mean, which is also 50%, we get a total of 100% or equal to 1. So usually finding area under the normal curve using mathematical formula is not easy. So usually the statistician they use a normal distribution table where they have approximated the area within certain limits. So here we have the standardized normal area table. So look at this figure. It is giving us the shaded area from 0 to any number z, and here the z is a positive number. So if we are interested in finding this area, this shaded area, so we can use this standard normal distribution table. So now since we are going to discuss several questions related to finding area under the curve, so we need to learn this standardized normal distribution table. So suppose we want to calculate the probability between 0 and 2. So probability that 0 is less than z, which is less than 2. So in order to calculate area from 0 to 2, so it means, let us draw the normal distribution. So here remember that this mean is 0, so we have 2 around here. So it means we are interested in finding this shaded area between 0 and 2. So in order to calculate this shaded area, we need to look up this number 2 in this table. So here we have the z values, so we need to look at the z value equal to 2. So here the first value is 0.0 and next is 0.1, and suppose we want to calculate 0.11. So the first two digits in this number, which are 0.1, we need to locate the first two digits downward, and the next digit, which is actually 0.01. So we need to locate the next digit on rightward. So suppose we want to locate 0.11, so it is actually 0.1 here and next 0.01. So 0.01 here. So just take the intersection of these two numbers. So this value is it gives us the area when z is 0.0438. So when z is 0.11, so this area will be 0.438. So this area is 0.0438. So this is between 0 and 0.11. But if we are interested in finding the probability or area from 0 to 2, so we need to look up this number 2 in this normal distribution table. So here is the number 2. So 2.0, and we need to look up, since there are no decimal points, so we can select this 0.00. So this value, which is the intersection of 2.0 and 0.00, so this is 0.4772. So it means the area between 0 and 2 is 0.4772, which is written here. So this is how we can use the standard normal distribution table. So now let us discuss few related cases. So since the normal distribution is symmetric, so the probability that random variable z lies between -2 and 0. So between 0 and 2 and between -2 and 0, due to symmetry, both probabilities will be same. So let me draw here. So here we have the mu 0, here we have the +2 point, here we have the minus 2 point. So from the symmetry concept, normal distribution symmetric, so area to the right of mean from between 0 to 2 is same as area between minus 2 to 0. So this area between 0 to 2, it is calculated to be 0.4772 or 47.72%. So this is 47.72%. So it means this area, it will also be equal to 0.4772 or 47.72%. So it means we can calculate probability within any 2 points using this standard normal distribution table and the concept of symmetry. So suppose we are interested in calculating probability that z is greater than 2. So this means we are interested in calculating this area. Remember that here z is 0, here we have z is suppose 2 at this point. So as far as this particular question is concerned, we are interested in calculating probability that z is greater than 2. So it means we are interested in finding this shaded area. So since we have the table which gives us the probability from 0 to any number, so but here as far as this particular question is concerned, we are interested in finding the area from number 2 onward. So question is how we can do how we can find this probability using the standard normal distribution table. So we can see that we know that normal distribution is symmetric, so this full area from 0 to onward plus infinity, this is 50%, so this full area is 50%, and if we subtract from this 50% this area between 0 and 2, which can be calculated by using this table. So instead of z, if we put 2, so we can calculate this area. So if we subtract area or probability from 0 to 2 from this 50% probability, we get the probability that z is greater than 2. So the same logic is used here. So 0.5 or 50% minus probability that z lies between 0 and 2. So from 0 and 2, so we can look up this table. So this is the value 0.2 and 0.00, it is 0.4772. So 0.5 minus 0.4772, we get 0.0228, or it is 2.28%. Now suppose we are interested in calculating probability that z is less than minus 2. So again draw the normal curve. So this is very important. So first draw the normal curve. Here mu is 0 and here we have minus 2. So now we are interested in finding this probability or this area that z is less than minus 2. Again we know that this full area to the left of 0 or left of mean, this is 50% or 0.5. So from this area we can subtract this area between 0 and minus 2 to get this shaded area. So 0.5 minus the probability minus 2 less than z less than 0. So in order to calculate area between minus 2 and 0, since the distribution is symmetric, so you can look up, instead of looking up minus 2, you can just look at plus 2 number. So just ignore the negative sign and look up the number with plus sign, which is plus 2. So it is 0.4772. Why we are ignoring the minus sign? Because the distribution is symmetric. So whether you use plus sign or minus sign, the area will be equal on either side of 0, which is mean. So here it is 0.4772. So 0.5 minus 0.4772, we get 0.0228 or 2.28%. So you can see that probability that z is greater than 2, it is same as probability that z is less than -2, and both are equal to 2.28%. So now let us consider another case. So suppose we are interested in calculating probability that z lies between -2 and +2. So here is the mu 0, here we have -2, here we have +2. So we are interested in finding this shaded area between -2 and +2. So in order to calculate this area, we can write it as from -2 to 0 and then 0 to +2, and then we will add these two areas together. So probability -2 less than z less than 0 plus probability 0 less than z less than +2. So now we need to look up this -2. So since the distribution is symmetric, so just look up +2 in this table. So +2, and since there are no numbers after this, no decimal point after this number 2, so it means we need to look up 0.00. So this intersection is 0.4772. So just write it here, and again here between 0 and 2 we need to look up the same number which gives the same probability or same area, that is 0.4772. So sum of these two is 0.9544 or 95.44%. So now let us calculate the probability that z lies between +1 and +2. So just draw the bell-shaped curve. So here is the mean, which is 0. Here is we have +1, here we have +2. So now we are interested in finding this area between +1 and 2. So in order to calculate the area between these 2 points, so you can see that we can write this probability 1 +1 less than z less than +2 into 2 parts in such a way that we will first find this probability from 0 to 2 using the same logic, just replacing z by 2. So, and then from this full probability we will subtract this portion from 0 to 1. So if from this area from 0 to 2 we subtract the probability or area between 0 and 1, so we get this shaded area. So the same logic has been used. So this is equal to probability that 0 less than z less than +2 minus probability 0 less than z less than +1. So for this area just look at 2, which is 0.4772, and then in order to calculate this area look up +1 in the table. So here we have 1.0, and since there is no number in the decimal point, so we need to use this 0.00, so it is 0.3413. So just subtract 0.3413 from 0.4772, we get 0.1359 or 13.59%. So suppose we are interested in calculating probabilities that -2 is less than z, which is less than -1. So first draw the normal curve. So here z is 0, so mu of z is 0, and now -2 and -1. So here we have -2, here we have -1. So now we are interested in finding this area. So again, in order to calculate this area, we will find this probability between -2 and 0, and then from this we will subtract the probability between -1 and 0. So if we subtract this probability, we get the required shaded area. So we can write it as probability -2 less than z less than -1. This is equal to -2 less than z less than 0 minus probability -1 less than z less than 0. So in order to calculate this area, so just look up 2 in the standard normal distribution table. So corresponding to number 2 we have 2.00. So the required probability or area is 0.4772, and then corresponding to this -1, just ignore the minus sign, so look up +1, so 1.0, so it is 0.3413, so just subtract, you get 13.59%. So let us consider another case. So suppose we are interested in calculating probability that z is greater than 1.96 plus 1.96. So let us draw the normal curve. So here the mean is 0, so z is equal to mu, which is 0. So here we have, remember that these curve will never touch, so it is 1.96. So now we are interested in calculating this area, that z is greater than plus 1.96. So in order to answer this question, we know that the total probability or total area to the right of mean 0, it is 50%. And if we subtract from this 50% the probability between 0 and 1.96, so we will get this shaded area, which is the required probability. So probability z greater than plus 1.96, so it is equal to 0.5 minus the probability between 0 and plus 1.96, so 0 less than z, which is less than plus 1.96. So now look up this number in the standard normal distribution table, which is 1.96. So it means we need to look up 1.9 here, and then we have this 0.06. So here we have 0.06. So 1.9 and 0.06. So this is the required number, which is 0.4750. So 0.4750. So subtract this number from 0.5, we get 0.025. So now suppose we are interested in calculating probability that z is less than -2.15. So in order to calculate this probability, just draw the normal curve. So remember that these should not touch. So here z is equal to its mean, which is 0, and we have -2.15. So we are interested in finding this area. So again we know that this is 50%. From -infinity to 0, it is 50% or 0.5. If we subtract this area from -2.15 to 0, from 0.5 we get the desired shaded area. So it is equal to 0.5 minus probability -2.5 less than z less than 0. So in order to calculate this probability, just ignore the minus sign and look up this number 2.15 in the standard normal distribution table. So 2.15, here we have 2.1 and then 0.05, this one. So just look up these two numbers. So the required area is 0.4842. So just subtract this number from 0.5, we get 0.0158, or it is 1.58%. So this is how we can use the standard normal distribution table to calculate different probabilities. So now let us discuss the general procedure for finding probabilities under the normal curve. So to find probability that A is less than x, which is less than b, where x is a random variable which follows normal distribution with mean mu and variance sigma square. So first step is draw the normal curve for the problem in terms of x. So first draw a normal curve. in terms of x. So here x will be equal to its mean. So here we have x minus infinity, here we have x plus infinity. Next step is translate x values to z values using this relation, which is z is x minus mu over sigma. So here z will be equal to its mean, and now the mean of z is 0. So remember that this mu is different. The mean of z is, you can use different symbol, mu dash or mu 1, or you can use any other symbol. So now the random variable z has been standardized, so its mean is 0. Next step is use the normal table to find the probabilities. So suppose you want to find, here we have x equal to certain value x naught. Suppose we are interested in finding this area. So here is the z scale corresponding to this number. So we will convert this x naught to some z naught, and we will use the table, normal distribution table, to calculate probability between 0 and z naught by using the normal distribution table. So this is the general procedure for finding probabilities under the normal curve. So now let us discuss few examples. Suppose x is a random variable which follows normal distribution with mean 8 and standard deviation 5. So question is, find probability that x is less than 8.6. So remember that the first step is to draw the distribution of random variable x. So just draw the normal curve for random variable x. So here mean is 8, so mu is 8, and standard deviation is 5. So mu is 8 and standard deviation is 5. So sigma is 5. So here the highest probability occurs at mean, so x is equal to its mean, which is 8. Now question is, find the probability that x is less than 8.6. So we have 8 here, so 8.6 will lie to the right of this x equal 8. So here we have 8.6. So question is, find the probability that x is less than 8.6, or in other words, we are interested in finding this shaded area in red color. So next step is to convert the x values into standardized form, the z values, by using this relation. So z is x minus mu over sigma. So x is 8.6 minus mu 8 and sigma is 5. So 8.6 minus 8, we get 0.6 divided by 5. The result is 0.12. So just draw the bell-shaped curve for the this new standardized variable with mean 0 and sigma 1, and now corresponding to this 8 we have 0, and corresponding to 8.6 we have 0.12. So we want to find the same area, only the scale has changed. Instead of finding probability that x is less than 8.6, now we will find probability that this z is less than 0.12. So corresponding to 8.6, the standardized number is 0.12. So now in order to find this area, we know that area to the left of this 0 or left of mean, it is 50% or 0.5. And then we can calculate this area between 0 and 0.12 by using the normal distribution table. So 0.5 plus probability 0 less than z less than 0.12. So just look up 0.12 in the normal distribution, standard normal distribution table. So you will get 0.0478. So just add these two numbers, we get 54.78% or 0.5478. So this is how we can calculate probabilities corresponding to normal distribution. So now again we have the same data that x is a normal random variable with mean 8 and standard deviation 5. Now this time we are interested in finding the probability that random variable x lies between 7.4 and 8.6. So again, first step is to draw the normal curve corresponding to this x variable. So here x is equal to its mean, which is 8, and now the two values are 7.4 and 8.6. so here we have 7.4, here we have 8.6, and we are interested in finding area between 7.4 and 8.6. So next step is to calculate the z values. So corresponding to this 8, the z value is 0. So we can use this formula. So in order to convert this 7.4 in terms of z value, so I'm using the same formula. So z is x minus mu over sigma. So I'm labeling this value as x1. So z1 will be x1 minus mu over sigma, where x1 is 7.4 minus mu 8 divided by sigma 5, we get minus 0.12. So corresponding to this value we have minus 0.12. And now corresponding to 8.6, again use this formula. So x2 minus mu over sigma, 8.6 minus 8 over 5, we get plus 0.12. So corresponding to this we have 0.12. So we are interested in finding the shaded area, but now the variable x has been transformed into standardized variable z. So probability that 7.4 is less than x, which is less than 8.6, it is written in terms of z as minus 0.12 is less than z, which is less than 0.12. So in order to calculate this probability, we can calculate this probability from minus 0.12 to 0, and then from 0 to 0.12. So you need to look up this 0.12 by ignoring the sign in the standard normal distribution table. So it is 0.0478, and similarly this 0.12 it is the same area or same probability. So just add these two numbers together, we get 0.0956, which is 9.56%. Okay, so far we calculated probabilities corresponding to some given value of x. That what is the probability that x lies between a and b, or what is the probability that x is greater than 2, or x is less than minus 1, or x is between minus 2 to plus 1, etc. But now we are going to cover the questions that finding the x values for a known probability. So in these types of questions we have the probability, we know the probability, and we want to calculate what is the particular value of x below which let's say 10% of the probability lie, or what is the particular value of x above which let's say 60% of the probability lie when x follows normal distribution with mean let's say 50 and standard deviation 10. So now we are going to discuss few questions in which we need to find the value of x, but we know the probability that how much probability will lie within two values of x. So let me explain it in different way. So finding the x values for a known probability. So given that probability between any 2 points is let's say 70%. So what are these those 2 points? So or what is a specific value of x below which 60% of the probability lie, or what is the value of x above which 10% of the probability lie. So it means in all these examples we are interested in finding the particular value of x where we know the probabilities. So this is also called inverse use of normal table. Let us review the main concepts which we have discussed in today's lecture. So in today's lecture we have discussed the concept of cumulative distribution function, and then we have discussed how we can calculate area under the normal curve, and then we have also discussed the standardized normal distribution, and then we have discussed some of the related examples. So in next lecture we will discuss how we can calculate area under the normal curve using MS Excel software package, and then we will discuss normal approximation to binomial distribution, and then we will also discuss some of the related examples. So till then, Allah Hafiz.